Hey, what's up guys? This is Dr. Vivek Palipuram bringing you the next lecturette in ECPE 127 random signals. In this lecturette, I'm going to introduce you to conditional probability density functions of random variables with respect to the other random variable. So in this case, we'll be interested in finding the conditional PDF of x given y, and similarly, we'll be interested in finding the conditional PDF of y given x. Both of these conditional PDFs can be obtained using the joint PDF. Let's take a look into how we can obtain these conditional PDFs. So to obtain the conditional PDF of x given y, I use this formula. PDF or the joint PDF of x comma y divided by the marginal PDF of y. Notice how similar it is to the conditional probability formula. So probability of A given B is equal to probability of A intersection B divided by probability of B. So this formula is quite similar to that one. I can also obtain the conditional PDF of y given x by applying this formula, the joint PDF of x comma y divided by the marginal PDF of x. One important thing to notice here is that unlike your other conditional PDFs that are conditioned by events, this new conditional PDF is going to have the same region of non-zero probability as the joint PDF. It doesn't change. We should always remember that, because ultimately the conditional PDF of a random variable with respect to the other depends on the other random variable. Essentially, it uses the same region of non-zero probability as its joint distribution, unlike the conditional PDFs obtained by conditioning on an event whose non-zero probability region is actually NZ intersection event B. So always remember, for conditioning a PDF or conditioning a PDF for a given random variable with respect to other uses the same non-zero probability region as its joint PDF. And I'm going to show this by example so it will become much more clearer. So let's take an example here. I have my joint PDF. It's equal to 2 for this region of non-zero probability, and I need to find the conditional PDF of y given x and conditional PDF of x given y. What I'm going to do is I'm going to focus on finding the conditional PDF of x given y, and then I'm going to solve some statistics based on that. And then I'm going to give you an in-class participation problem for Wednesday's class and for Friday's class. So let's first focus on finding the conditional PDF of x given y. So conditional PDF of x given y is obtained by f of x comma y divided by the marginal PDF of y, and NZ is same as fx comma y. So in this case, I need to get the marginal PDF of y first, which is obtained by the conventional methods that I have taught you so far. The joint PDF in this case is equal to 2 for this region, and it's equal to 0 otherwise. So first, I need to draw the region of non-zero probability. This is the line y is equal to x. And I'm interested in the region y is less than or equal to x. And you can convince yourself that all the points that are below this line actually correspond to this region y is less than or equal to x. So this is my region of non-zero probability. First, I need to find the marginal PDF of y, which is typically obtained by integrating the joint PDF with respect to the other random variable x from negative infinity to infinity. But in this case, because I have a non-zero probability region that does not span over negative infinity to infinity, I need to ask myself, hey, for any x, how does, or rather for any y, how does x vary? So here, for any y, x varies from this point where x is equal to y all the way to this point where x is equal to 1. So the limits of integration will be from y till 1. Now I'm integrating the joint PDF here, whose non-zero probability region is given by this equation right here. Now because I'm integrating x out, I'll eliminate the fx of x in this case, and all that will be remaining is the marginal PDF of y, which is valid for, or which is non-zero for this region. So I get f of y as 2 times 1 minus y for y between 0 to 1, and this is equal to 0 otherwise. Now the conditional PDF of x given y now is 2 over 2 times 1 minus y for 0 to y to x to 1, and it is equal to 0 otherwise. notice that the region of non-zero probability for this conditional PDF is going to be the same as the original NZ, unlike conditional PDFs that are conditioned by events. So that's the probability model for the conditional probability density function of X given Y. We can also obtain expected value of a random variable that are conditioned by the other random variable. So for example, if I want to find the expected value of some function of X comma Y given the random variable Y, so I need to use the conditional PDF of X given Y here. I'll integrate it with respect to X typically from negative infinity to infinity. But in reality, these limits will be dependent on NZ, the region of non-zero probability. Let me use the previous example and find out the expected value of X given Y. So expected value of X given Y is integration from negative infinity to infinity, X times f of X given Y. So this is some function of X comma Y times dx. Now the reason why I'm integrating with respect to X is because f of X given Y is actually a probability model for X. And that's why in order to find its expected value of X, I need to integrate it with respect to X. So let's integrate that conditional PDF. The conditional PDF that I obtained was 1 over 1 minus Y. Let me just verify it. Yes, it is 1 over 1 minus Y for this region. And it is equal to 0 otherwise. So expected value of X given Y is equal to some Y is integration X times 1 minus Y dx. And the limits of integration will depend on the region of non-zero probability, which is this one right here. So let me plot that region of non-zero probability one more time. And here my limits will be for any Y, X varies from Y to 1 in this region. So the limits will be from Y to 1. So I'll get the expected value of X as X squared over 2 times 1 minus Y. The limits are from Y to 1. When I plug in a Y, I get a 1. When I plug in a 1, I get a 1. When I plug in a Y, I get Y squared or 2 times 1 minus Y. The numerator term can be written as 1 minus Y times 1 plus Y, or 2 times 1 minus Y. So 1 minus Y and 1 minus Y will cancel each other out, giving me the conditional expected value of X given Y as 1 plus Y over 2. So for example, let's say that for some reason Y is equal to 2, or rather Y is equal to 0.5, because Y can never exceed 1. The expected value of X will be 1.5 over 2, which is 3/4. So that's the principle of conditional PDFs of random variable with respect to the other random variable. In summary, you'll still apply the formulas that are quite similar to the conditional probability formula themselves, and you will use those conditional PDFs for evaluating the expected values of these different random variables. For Wednesday's in-class participation problem, here's what I would like for you guys to do. For Wednesday's class, I would like for you guys to give me the conditional PDF of Y given X, a complete formula. And for Friday's class, you can give me the expected value of Y for any X is equal to small x, using the principles that we have seen in this lecture. So these are your in-class participation problems that are due for the next week. I'm giving you a respite from in-class participation problem this Monday. Okay. Adios, guys.